I don't want to push. Well, let's get started. I didn't mean to push record, but it's a good time to start, right? Good as any. So we are looking at derivatives as a rate of change. So you might be freaking out because you see that formal definition of derivatives. Well, we don't have to use it right now, but let's just go over it. We can use those techniques of finding derivatives that we've been learning recently. So let's just talk about this. The definition, instantaneous rate of change, doesn't sound like anything new, does it? So let's just read through it. The instantaneous rate of change of our function f with respect to x at x sub 0 is the derivative. So maybe it's a little different. We used a instead of x sub 0 before. The derivative of our function at that value x equals x sub 0 is equal to the limit as h goes to 0 of x sub 0 plus h minus f of x sub 0, and that whole thing is over h, provided again that the limit exists. So we are going to be talking and doing a little bit of applications with physics partly through this section. And we're looking at position functions, so a position of some particle or something, and how it's moving back and forth on a line with velocity. And so velocity is the instantaneous velocity is the derivative of a position with respect to time. So derivative of a position. So velocity, all we're going to do, if we are given the position function, we're going to take the derivative of that position function with respect to time. If the body's position at time t is, let's call it the function s or equal f of t, then the body's velocity at time t is the following. So this is just mathematical notation. We have some function v of t, our velocity function. We get that velocity function by, this is just saying that we're taking the derivative of the function, which is called s, with respect to the variable t. So s is just another way of writing the y value, well, of our point if we have y. So, and limit as, so this triangle t, this is the change in t, is approaching 0. Before we had that as h, right? So all this is we have a function. Let's say that we have some value here, t, and we're getting closer and closer that t, this change between, let's say this is t sub 0 and t. That change in here is going to 0. Where before we said this was h, as our h value got closer and closer and closer to 0, that gave us the instantaneous rate of change. And this is our change in t. So we want it smaller and smaller and smaller. So that limit as the change of t is going to 0 is equal to f of t plus delta t minus f of t all over delta t. So velocity is almost like speed. The only thing is that velocity is a vector. It gives us direction. Speed with direction. So let's look at the definition of speed. All it is the absolute value of your velocity function, right? So if we had a negative, our velocity was negative, so if v prime of t is negative, so less than 0, then the particle is going backwards. We move backwards. So if we get negative 60 miles per hour, we're moving backwards towards the beginning of 60 miles per hour. But that doesn't make sense, really, -60. So if we're talking about speed, we would be saying we are going 60 miles per hour. So you're just taking the absolute value of your velocity function. So acceleration, all that is we're taking the derivative of the velocity with respect to time. So we could be increasing our speed, but as we're going on, and we might be speeding up faster. And so speeding up faster, that's the acceleration. Or maybe we're still speeding up, but not as fast. And so this would be our acceleration. And so again, to get that, all we're going to do is we're going to take the derivative of our velocity function. So usually you'll see it as a sub t, that is denoting the acceleration. This is the derivative of our velocity function with respect to time. And this is a notation of saying the double derivative. So we're going to take the double derivative of our position function. And we had called our position function s. Another way to write that notation-wise, so the double derivative is s double prime of t. So the jerk, that is the derivative of the acceleration. So, you know, sometimes, have you ever been in a car, or I'm sure you've all been a new driver and experienced that kind of not sure of the acceleration and kind of jerk forward, or slamming on the brakes a little too fast? That's kind of like the jerk there. Okay, so knowing that terminology, let's go through and look at an example. So we talked about this up here, this velocity is less than 0, actually, and I put the derivative, which would have been my acceleration, so I'm glad I came back up here. So if our velocity is less than 0, then it moves backwards. If our velocity is greater than 0, the thing that's moving is moving forward. And then if our velocity is equal to 0, we're at a standstill. Okay, so now looking at an example. So given the position S, which we can call f of t, of a body moving on a coordinate line with s in meters and t is in second. So all we're doing is we're moving on some line here, back and forth, back and forth. Well, it depends on, is the velocity positive or negative? And we want to find the displacement. Oops, and I missed a piece in here that we need. It's given to us that our t value is between 0 and 6. So 0 is less than or equal to t, is less than or equal to 6. So we're ranging between 0 and 6 seconds. So given this position function, we want to find the body's displacement and the average velocity for the given time interval. Okay, so average velocity. Maybe just to help us, we could call this V F. But all that is, we looked at the change in our Y, but in this case, it's our change in our S value all over the change in our time. So if we look at this, we need to look at what is S of 0. If we put in 0 in here, we get 6 times 0 minus 0 squared, which gives us 0. So at time 0, our position is 0 meters. And then we want to see where are we after 6 seconds. And so let's look at S of 6. So going in and plugging in 6, wherever we see a t here, we get 6 times 6 minus 6 quantity squared. And so this would give me 36 minus 36, which is also 0. So right here, my displacement is how far have I gone from the 0 position. Well, if I'm starting at 0 and I'm ending back at 0, I haven't displaced that thing at all. And so the displacement is 0. So that doesn't mean that that particle or that item, whatever it is, hasn't been moving. So between 0 and 6 seconds, it could have gone forward here and maybe came back here and then came back here. And if that had happened, then if we're trying to find the distance that it occurred, then we would have to sum that distance up until we got back. But it just wanted our displacement. And it wants the average velocity. So we want to look at the change in our S value, our Y. Well, this is a point, right? At time 0, we're 0 meters away. At time 6 seconds, we were 0 meters away. And so if I look at this, I got 0 minus 0 all over 6 minus 0, which is 0 over 6, which is 0. So the average velocity is 0. Oops, I'm sorry. It wanted average velocity. That is not the average velocity. Yeah, it is. Let me just pause for a sec. Yes, we did that right, except this is in terms, we're going meters per second. Our denominator time was in terms of second. So we found the average velocity. We found our displacement. We really started at some place and moved probably back and forth and came back. We don't know if we went to the left of 0 meters or not, but find the body's speed. So to find the speed, we need to look at the velocity and the absolute value of the velocity. So if I want to look at v of t, remember v of t, this was equal to the derivative of our position function. So looking at this, we can use our shortcut. So the derivative of 6t with respect to t is 6 minus, and the derivative of t squared, bring our power down front to t and subtract 1 from our power. So this is going to be our velocity. And it wants to find the body's speed at the endpoints of our interval. So let's look at it. When we start at t equals 0 seconds. So v of 0 equals the derivative of our function with respect to 0, which is equal to 6 minus 0, which is equal to 6 meters per second. If I was looking at what's happening at 6 seconds, I'm plugging this into my derivative function for the position. So the velocity at 6 seconds, 6 prime of 6, if I plug this in, I get 6 minus 2 times 6. So this is 6 minus 12, which is equal to negative 6. And so the speed, though, is the absolute value of this. It's just that the direction we were going backwards. So this is equal to 6 meters per second. So that was finding the body speed at the endpoint of the, or one of the, or at the endpoints of the interval. The next question, though, says find the body's acceleration at the endpoint. And so acceleration, our a sub t value, this is equal to the derivative of our velocity, which we could write as the double derivative of our position function. And so we first want to figure out what the acceleration function is. And so taking the derivative of this velocity, this is equal to the derivative of our constant 6. Well, derivative of constant is 0 minus the derivative of 2t. So the derivative of 2t is 2. So this is equal to negative 2. So looking at this, I notice there's no t value left. My a sub t is equal to negative 2. So it doesn't matter if I plug in 0 here, or if I plug in 6, I'm still getting back negative 2. And I believe this meters per second squared. Okay, so we found out what the acceleration was at time 0 seconds when we started off, and at 6 seconds of that particle. And that was negative 2 meters per second squared. So next question is asking when, if ever, during the interval, does the body change direction? Well, we know that that has to be the case if we're coming back to 0. And so let's figure out where is it changing direction. Well, it's changing direction when the velocity is equal to 0. It's probably going to be changing direction. And we want to make sure, is our velocity positive and negative on each side of that 0? And if so, then it is going to be changing direction there. So looking at when our velocity is equal to 0. Well, this is our velocity function, v of t. Is 6 minus 2t is equal to 0. So let's solve for t there. Let's add 2t on both sides. We get 6 is equal to 2t. Divide by 2, we get t is equal to 3. So it's probably going to be changing direction at 3 seconds, which makes sense with our problem and our displacement. So if I look at this, and this was my time equals 0, and my time equals 6, and here is time equals 3, I want to know, is my velocity positive or negative at first? Well, again, I could probably tell by what's happening and being back here that it would have to be positive in this direction, but let's try it. So if I look at b of a number in between 0 and 3, so any number, and I'm really just curious, is it positive or negative? I don't care what the number is, but let's say we plugged in 1 into this velocity function, which was right here. And I get 6 minus 2 times 1, so 6 minus 2 is 4. This is greater than 0, so we're moving forward. And then I want to see, make sure that it's an opposite. And so let's look at when t is between 3 and 6. So maybe let's look at when it's 4. So if we go into our velocity function, we get 6 minus 2 times 4, 6 minus 8, that's negative 2. This is less than 0. So we've come forward here, and then we've moved back this direction. And so displacement from that home is 0. Okay, so another example, particle in motion. At time t is greater than or equal to 0, the velocity of a body moving along a horizontal s-axis is v equals t squared minus 4t plus 3. So be careful here when you're reading your problem. This is telling me our function we're given is v. I don't know what the position function is, and we won't be able to figure that out until the end of this course, where we can kind of go backwards, where we're given a rate of change and we can figure out what the original function is. So we're given the velocity, so that's direction and speed. And we want to find the body's acceleration each time the velocity is 0. Okay, so a couple things that we need to do here. We need to figure out when is the velocity equal to 0. And so we need to know when is this v of t equals 0. So set our equation equal to 0. We have t squared minus 4t plus 3. When is that equal to 0? Well, we're really lucky, right? Because this is pretty easy to factor. And so we have t minus 3 all times t minus 1 equals 0. So let me just pause for a sec. And so now looking at this, we can figure out what values of t make this equal to 0. So 2 minus 3 is equal to 0 when t is 3, so at 3 seconds. And t minus 1 is equal to 0 at t equals 1. And I'm just, for some reason, assuming seconds because of that last problem, but it doesn't tell me that this is seconds. Okay, so we found out where our velocity is 0, t equals 3 and t equals 1. Going back to the question, though, it says find the body's acceleration each time the velocity is 0. So we need to go back in and we need to figure out what is the body's acceleration. Well, we know acceleration is the same thing as the derivative of the velocity function. So a sub t is going to equal the derivative of our velocity. So the derivative of this function, derivative of t squared is just 2t, minus the derivative of 4t is just 4, plus the derivative of 3 is 0. And so we want to look at what is a sub 3. So going in here and plugging in 3 wherever we see a t, we have 2 times 3 minus 4, which is 2 times 3 is 6, 6 minus 4 is 2. So the acceleration at 3 units of time is 2. And the acceleration at 1 second, I'm sorry, for some reason I want to again call it seconds, 2 times 1 minus 4, which is negative 2. So we found the acceleration each time the velocity was 0. So this was part A. So we want to know when is the body moving forward and backwards? So again, that has to deal with the velocity. We need to find when is v sub t greater than 0 and when is v sub t less than 0. When is the velocity less than 0? When is the velocity greater than 0? Well, we did part of this work right here, right? We found out when our velocity is equal to 0. And so that was at t equals 1 and t equals 3. So let's look at this. So we want to test values. We want to see if we choose a number in between 0 and 1, and we plugged it into our velocity. Let me just write it down here again. V sub t equals t squared minus 4t plus 3. We want to see, is this positive or negative? Technically, I really don't care what the value is again, but I just care if it's positive or negative. So if I choose a number between 0 and 1, so how about 1/2? And I plug it into my velocity function, I get this is 1/2 quantity squared minus 4 times 1/2 plus 3. So 1/2 quantity squared is 1/4. 1/4 minus 4 times 1/2 is 2, so minus 2 plus 3. So I notice here that 1/4 plus 3, 3/4, 3 and 1/4 minus 2, this is greater than 0. So it's moving forward in this piece. So let's see what's happening between 1 and 3. So between 1 and 3, let's choose some number. And so how about 2? So we have v of 2 is equal to 2 squared minus 4 times 2 plus 3. So simplifying that out, I have 2 squared is 4 minus 4 times 2, which is 8, plus 3. So that gives me -1. This is less than 0. And so since it's less than 0, we're going to be going backwards. And then just test something bigger than 3, anything bigger than 3. So how about 4? So if we plug in v of 4, we would get 4 squared minus 4 times 4 plus 3. So that gives us 16 minus 16 plus 3 is positive. This is greater than 0. And so we know then it is going forward again. So we found out when the body is moving forward and backwards. So maybe we should write that out. So it's going forward on the interval from t is, and there's a couple ways we can write this, 0 is less than t is less than 1, union t is bigger than 3. I would probably normally write that in interval notation, 0 to 1, union 3 to infinity. And then it's moving backwards on 1, between 1 and 3. Or 1 is less than t is less than 3. So to find when our velocity is increasing and when our velocity is decreasing. Well, notice that, remember when we, derivative is just the slope. So we want to know when is our slope positive for our velocity and when is our slope negative. I think we just kind of did that. So when it's moving forward, it's increasing. Sorry, no, we did not. We need to take the derivative of our velocity function. I need to look at the derivative of the velocity. So going to our velocity function, we already took the derivative. That was our acceleration function, which was 2t minus 4. And in order to find when this is positive and negative, let's find out where this is equal to 0. So 2t minus 4 is equal to 0 at what time? Well, if I add 4 to both sides, I get 2t is equal to 4. And if I divide through by 2, I get t equals 2. And I want to know is at 2, between 0 and 2 and up on 2 to infinity, is this velocity function positive or negative? And so again, you need to test values in these intervals. And so I need to choose a value that comes between 0 and 2. So if I plug that into my velocity function, how about plugging in 1? Oops. My velocity derivative is 2t minus 4. So plugging in 1, I have 2 times 1, which is 2 minus 4 is negative 2. So this is decreasing. My velocity is decreasing here. And then let's look at what's happening after t equals 2. So if you choose a number greater than 2, so how about 3, and plug it into this derivative of the velocity, I have 2 times 3 is 6, minus 4 is 2. So this is greater than 0, so the velocity is increasing. Okay, so our next example, so we have a lunar projectile motion. Maybe this one day will happen when we'll be on the surface of the moon ourselves. We're taking a vacation there. Who knows, with technology today, that's totally a possibility, right? Anyways, a rock is thrown vertically upward from the surface of the moon at a velocity of 24 meters per second, about 86 kilometers per hour, if we want to rewrite that in terms of kilometers per hour, reaches a height of s equals, so the position, the height, is 24t minus 0.8 t squared meters, and t equals seconds. So part A, find the rock's velocity and acceleration at time t. That's not too bad, right? So we're given our position function, and we know to find our velocity function, all we're doing is we're taking the derivative of our position. I'm just making sure I started the video. And I probably did, but okay. Sometimes I'm worried I forget. So S of t, we want the derivative of this. This is going to equal my velocity. So the derivative of 24t, that's equal to 24, minus the derivative of 0.8 t squared. So we have this 0.8 times our exponent, which is 2t. Subtract 1 from our exponent, it's just 1. So our velocity function is 24 minus, well, ignore your decimal for a second. 2 times 8 is 16, and then we're going to move it over 1 to the left, so that's 1.6 t. Okay, so we got part of A done. And now we need to find our acceleration function. And so we know acceleration, A sub t, this is equal to the derivative of our velocity function, which we have above. Its derivative of 24, constant is 0, minus derivative 1.6 t is just 1.6. And so we have our acceleration function, which is just a constant, negative 1.6. Okay, so that was part A. Part B, how long does it take the rock to reach the highest point? Well, if you look at our function, it's a quadratic. So I know that's a parabola, right? So I'm throwing the rock up. It's going to hit some position and it's going to come down. And I know that my coefficient, my number in front of my t squared, remember that told us if I was pointing up or downwards. And this is negative, which means my parabola faces down. And if that was opposite, then I'd be a little bit worried, but it's not. And so we need to figure out what is this point right here. And so there's a couple ways that we could do that. We can use algebra, figuring out what the vertex is, and we should be able to find the vertex given a quadratic. Or remember what is happening here when it's changing direction. We know what's happening there when it's changing direction is that our slope changes, our instantaneous rate of change at that point is 0. And so we kind of want to know, we either need to find the vertex of S of t or find when our derivative f prime of t is equal to 0. And so I'm looking at when is 24 minus 1.6t equals 0. So if I add 1.6t to both sides, I have 1.6t equals 24, divide by 1.6. I get 24 divided by 1.6 is 15. So talking about my problem, it's in terms of seconds. And so to me, that's telling me it's reaching its highest point when t is 15 seconds. Okay, well, then I want to know how high does that rock go? Well, I have my position function. My position function s of t, or s, is equal to 24t minus 0.8 t squared. So I want to look at what is s of 15. So this is 24 times 15 minus 0.8 times 15 squared. So throwing that in the calculator really quickly. We get back 180. And going back to my problem, I'm talking about meters. So meters. Hi. So it occurs, max height occurs when t is 15 seconds and it's 100 meters high. Okay. Then it wanted to know, part D, how long does it take the rock to reach half of the maximum height? Okay, well, we know what the maximum height is, right? It's 180 meters. So for part D, half of the maximum height, 180 meters, would be 90 meters. So we want to know how long does it take the rock to reach half of its maximum height? Well, it's going to be two places where that's going to hit. It's going to come up and it's going to hit halfway here at some time, t. And then when it's coming back down, it's also going to hit that half mark. Okay, so that means our position. We're looking at our position function again, and we want to know when is our position function, which is height of that projectile. equal to 90. So we want to know when is 24t minus 0.8t squared equal to 90. So looking at what type of equation I have a quadratic. So solving quadratic equations, we need to get that equal to 0. And so if I add a 0.8t squared to both sides, I get 0.8t squared. Subtract 24t, so minus 24t equals 90. So I just moved everything to the right hand, plus 90 equals 0. So I just moved everything to the right hand side of that equation. And now we need to figure out when that's equal to 0. So I can throw this into the quadratic formula. I can try to manipulate this and see if I can factor it. I don't like the 0.8 decimal. I don't like that decimal in there as a coefficient. I could clear that by multiplying by 10 on both sides, but then I have huge numbers. I think I would deal with the quadratic formula. Okay, so t equals negative b. So that would be positive 24 plus or minus the square root of b quantity squared. So negative 24 quantity squared minus 4 times a. So my a value is 0.8 times c, which is 90, all over 2 times a, which is 0.8. Let's go through and figure that out. I'm just going to pause the video while I plug in the calculator. Okay, so plugging that into the calculator, we get that it was 25.6 seconds and 4.4 seconds, which when we were talking about what's happening graphically, we knew that it was a max height at 15 seconds. So we should get it, it's reaching halfway before that, which was our 4.4. And we talked about it hitting it on the way back down. And that was 25.6. The last piece is wanting to know how long was that rock in the air? How long is the rock aloft? And so we need to know how long. We want to know when are we hitting the ground here? What time is that at? And so we need to look at our position function, which we know what it is, s of t, which is t minus, actually, let's just pull it up. It was 24 minus t. 24t minus, 0.8 t squared. So we want to know, when is this equal to 0? When is it going to hit the ground? Okay, so I notice really quickly that there's things that I can factor out there. I know 8 goes into 24, and I see a t and a t squared that both have something in common. I don't like the decimal again, so I might just clear my decimal, and we can do that by multiplying both sides by 10. So I get 10 times 24t is 240t. Minus 10 times 0.8, so that's just 8t squared, equals 0. So let's factor out an 8 and a t. So if I pull an 8 out of 240, I'm left with 30. I took out all the t's there, minus, and pulling out 8t from 8t squared, I'm just left with a single t, equals 0. So 8t equals 0 when t is 0. And 30 minus t is equal to 0 when t is 30. And so it's going to take 30 seconds from when we launch the projectile and it comes back and it hits the ground. Oops. So the number of gallons of water in a tank, T minutes after the tank has started to drain, is the following. So we're given Q of T is equal to 200 times the quantity 30 minus T. That quantity is squared. So how fast is the running water or water running out at the end of 10 minutes? Okay, so this is the number of gallons of water in the tank, which is our Q of T function. It wants to know how fast. It wants to know the rate that that is running out at 10 minutes. So when we're trying to find the rate, how fast something is going, we're looking at the derivative. And so we want to look at the derivative of this function Q of T. The thing is that Q of T is 200 times this 30 minus T quantity squared. We haven't learned how to use this chain rule yet where we can do that. So we either need to write this as a product, 30 minus T all times 30 minus T. And we can use our product rule of derivatives, or we can distribute things out, and that might be faster. It doesn't matter, we'll get the same result. So keep that 200 out front. Let's first FOIL out 30 minus T times 30 minus T. Well, 30 times 30, that's 900. We're going to have a negative 30T and a negative 32T, so that's a minus 60T. And then a negative T times a negative T is plus T squared. So I'm just going to distribute my 200. And as I distribute my 200, I'm going to rewrite this in descending order of a power. So 200 times T squared, that's 200 T squared, minus 200 times 60T. Okay, well, 2 times 6 is 12, and I have 3 zeros. So that's 12,000 T. So minus 12,000 T. And then I have a 200 times a 900. So I think to myself, 2 times 9 is 18. How many zeros do I have? I have 4. So that's 180,000 T. So we have where we can find how many gallons are in the tank after T minutes. We want to know what is that rate though? How fast is it running out at T minutes? So let's just find the derivative first. That way, if we have to answer any other questions, we can. So looking at the derivative of Q of T using our general power rule. So 200 T squared, the derivative of that is 400 T, minus the derivative of 12,000 T is 12,000. And derivative of constant is 0. So now let's look at Q of 10. So we have 400 times 10 minus 12,000. 400 times 10 is 4,000 minus 12,000, which is equal to 8,000. Let's think about, and that's a negative 8,000. So it's decreasing. We knew it was going to be decreasing because the water's pouring out. So that negative is telling me it's decreasing, and it's decreasing by, think of this if you want as a fraction. So our Q of T, which is our change of Q, is gallons. So gallons. And our numerator is in terms of minutes. So it's decreasing by 8,000 gallons per minute at 10 minutes. So what is the average rate of which the water flows out during the first 10 minutes? Well, if I was looking at that average rate of change between 0 and 10 minutes, I would have to look at how much water is there at time 0. So plugging this into my function, maybe this is the easier one to plug it in right now. When T is 0, I have 200 all times 30 minus 0 and then squared. So this is 200 times 30 times 30, that's 900. This is 180,000. So at 0 minutes, there's 180,000 gallons of water in that tank. And then let's look at how much water is in there at 10 minutes. So plugging it into my Q of T function, Q of 10 is 200 30 minus 10 quantity squared. So this is 200, 30 minus 10 is 20, squaring 20, so that's 200 times 400. So this is 80,000. So I have a point 10 minutes. There's 80,000 gallons left in my tank. So now I'm looking at my average rate of change. And so the average rate of change the change in my number of gallons, so 180,000 minus 80,000, all over 0 minus 10. So 180,000 minus 80,000, that is 100,000 divided by negative 10. That gives me negative 10,000. And this is the number of gallons per minute. So if I looked at the average rate of change between the 0 and 10 minutes, it's pouring out about negative or 10,000 gallons per minute. Exactly at 10 minutes, the instantaneous rate of change is only 8,000 gallons per minute. So we can kind of think of that, it's slowing down how fast it's coming out of the tank.